Good evening and hello, welcome back to Let's Code MS-DOS. And today we're going to learn how to do split screen in VGA. Split screen is being used in a couple of games actually. The most famous games that come to my mind are Pinball Dreams and Pinball Fantasies. You can already see this here running on archive.org in its MS-DOS emulator, web-based emulator. And the pinball simulator is actually very clever because it was originally written for the Amiga, which can do such things with ease with its custom chips. But the VGA card is actually pretty difficult to convince to do all this smooth scrolling and animations, and especially the scoreboard here at the bottom. On the Amiga, the scoreboard is at the top, and that actually shows a little bit how this works. The VGA card can scroll smoothly. We did that in a previous video in text mode, but it also works in mode X and mode Y. And you basically just set the CRT register, which is the start address low and high. We will come to that in a second. We set that to the desired starting point in memory, and with that you can already get a very smooth vertical scrolling, which is what they're doing here. But the extra scoreboard here is actually a bit problematic because you would have to copy that over the area that is being scrolled, and that's very slow and inefficient. But the VGA card has a split screen functionality in the CRTC register 18 hex, which is the line compare register. This can be set to an arbitrary scan line, and in mode X and Y we have line doubling. So in mode Y we have 400 vertical lines, and in mode X 480 vertical lines. So you can set that to, I don't know, 360 or something and get 40 pixels of split screen state. How does that work? The line compare register, when the line number that is being set in here is hit, it will reset the video start register, basically, or copy of that, back to 0. So it will jump to the front of the memory, which means that in memory, this here is actually the start of memory, and the table graphics, for example, is starting a little bit later in VGA memory, so that you don't see the scoreboard again if you scroll up to the top of the table. The other animations here, like the flashing lights, are all palette manipulations. It's basically color cycling, which is also super efficient. This allowed Pinball Fantasies and Pinball Dreams to run even on 286. I think Pinball Fantasies runs on 286. The earlier version was a bit less efficient, and I think required something more towards the 386. Yeah, you can also use this for a number of other uses, but Jazz Jackrabbit also uses it for the score and weapons display at the bottom of the screen. I think Hook, the adventure, was one of the few adventures to use hardware horizontal scrolling and the split screen for the inventory. Looks very neat, but for example, Lucasfilm never used that on their adventures, even though it might have made sense. But enough of that, I would say. We need to learn 3 things today, or a couple of more things. We need to learn about the line compare register, the start address high and low register, and then there are 2 more registers, the overflow register and the maximum scanline register. Because if you think about it, the line compare register only has 8 bits, which means you can only address up to 255 lines, which is not enough, not even enough for mode X or Y, which have, as I said, 400 or 480 lines because of the line doubling. So you need up to 2 additional bits, and the 2 bits were stuffed into registers that had empty bits on the EGA card. Or CGA, I don't know. Might be that this already works in EGA. I'm not quite sure. Haven't tested that, but it for sure works on VGA cards. So one is the overflow register. It has a bit number 4, which is called LC8, which is the line compare bit 8. That's actually the 9th bit, because we're starting to count at 0. And then we have the maximum scanline register, which has bit 6, which is LC9, which is bit 9 of the line compare field. All in all, we thus have 10 bits to work with, so we can count up to 1024 lines, which is quite a lot, obviously. All right, so let's look at the program. I filled in a couple of things already. The sign generation I already used. We are going to have a sign motion for the split screen so that we can slide an image in front of a different image in a smooth fashion, in a sine wave. A couple of function stubs and a couple of variables that we will need. It's our usual framework that we are always using in this series. So first of all, we will initialize the sign tables. That's already coded. We will clear the screen just so that the text screen is empty, because we will have an indicator for the loading of the GIF images that we're using. We're using our GIF loader that we coded a couple of years back. So I drew a couple of very simple images in Deluxe Paint. And the first one that we're going to load is, actually doesn't matter, is let's code 2.gif. We're going to load that. I forgot what the (0) is for, but past me probably knows, and I have to specify that, I don't know. And the background image will be called let's code 1.gif. All right, if either of these fails to load, the pointer will be null, so we'll check that. Image background equals null. Then we will print something along the lines of couldn't load image, %s. We don't have an s here, so couldn't load image. And you have to deal with that. That's okay. And then we just exit gracefully. And that's it. If we were able to load the stuff, then we set mode Y, 200 lines. That is nice. With mode Y, we have up to 4 screen pages, or the respective number of lines vertically that we can scroll. Then we need to call a function called init overflow registers, because we have to manipulate the maximum scan line and the overflow register, and we only want to toggle bit 4 and bit 6 inside of that. So at the beginning, after mode Y, we will read out this register and store all the other bits, and only toggle the bit that we want to change. So that's what we're doing here. We could do that every time we render a frame, but this means we have to do another port operation, which is expensive. And since these bits are never changed, should never be changed during mode Y being active, because it's the, for example, it's the vertical retrace start and end. These are video timings that should never change, especially also with the other stuff. And the same with the maximum scanline register, which has the scan doubling, the start vertical blanking, and the maximum scan line. That should also not change. So it's safe to assume here that these are const, basically. Then we set the start address into memory to page 2, and we do that by setting it to 16,000. Why 16,000? Because the VGA card works in 32 bits internally. That means 4 pixels are always accessed at a time, which makes it pretty fast, but which also means that we can set the start address only in multiples of 4. So if we set 16,000, we jump to pixel number 64,000, which is the start of the second screen page, which means we can fit a whole image into screen page 0, which will then be used in the split screen operation to reveal it bit by bit. All right, that will do. Then we will set the palette to arbitrarily to the one from the foreground image, which is just something I decided on a whim. The images have almost the same palette, except I used 2 different Deluxe Paint fonts, so the fonts should have actually different colors, but Deluxe Paint always uses the same palette space, so yeah, you won't notice it. Then, after loading, I also want to implement 2 new functions. One function is called Shuffle Frame, which takes the image data of an image and copies that into a buffer in a shuffled manner so that the pixels are arranged in the same way that they are in mode X and mode Y. That is, interleaved by the bit planes. So every 4th pixel has the correct bit plane, and we can basically, or that's how it is actually in memory, but we will now shuffle it so that first we only get bit plane 0 pixels, then bit plane 1, 2, and 3. This way we can use memcopy and only switch 4 times the page registers, which is much faster than any other copy. And then we will do a special new function called ShuffleBlit, which assumes that the buffer is already shuffled. So we take this newly shuffled buffer and we copy it to VGA page 0. This is the foreground image that is being shifted into view due to the split screen. And then we do the same with the background image, and we'll copy that to page 1. VGA page 0 and 1 were already defined in the VGA header. You can have a look at that. It's basically just the offsets into VGA memory where the actual pages start. And then we do our usual while not do quit routine, infinite game loop, so to speak. And if the user has hit any key, then we clear the keyboard buffer and we set do quit to 1, so that on the next iteration we will gracefully quit this thing. Then we'll wait for the vertical retrace so that any operations that we do on the split screen happens during the blank interval, so the person sitting in front of the screen doesn't see any tearing or anything. And then we call the setSplit function, and the split will be according to the sign table, and the sign table has 512 entries. And that's it. And then we increment our time variable, and we have a nice animation. That's the whole deal. We now have to implement all the stuff, and I'm going to start with the VGA functions first. Already put the stubs in here, shuffle frame and shuffle blit, and they're actually rather simple. We need a couple of run variables for the for loops. We will have a far pointer for the input pixels and a far pointer for the output pixels. Then we have an outer loop iterating over all the pages, actually. We have 4 pages on the VGA card, or bit planes in this case. And we also iterate over all the pixels in the bit planes. So for j equals 0. And we also initialize the input pointer with the start of the input buffer that we got, and the output pointer with the output that we got plus 16,000 times I. which means exactly what you see here. It's the different pages, basically, or sections of the graphics in memory. Okay, that's that. Then, oh, I closed that way too early. Then we do that until we are at 16,000. And then we have to increment a whole lot. J has to be incremented. Pin will be incremented by 4 because we always read every 4th pixel. And then P out gets incremented normally because that's actually linear. And that's it. The only thing that we do here is actually copying stuff into Pout, and namely the stuff that we are reading from Pin. So this is a pixel-wise copy, basically, of every 4th input pixel into the output buffer. And that is then properly shuffled, so to speak. That's all there is to this function. You can delete this. And then the shuffled blit is very simple. We have a byte P, which is again the counter for the screen pages, basically, or bit planes, whatever you want to call that. And we increment that. And then we write a byte to the sequence controller, to the index port, and there the map mask register. That is controlling which bit plane is actually currently active. So we write to the data after that, and this is then just writing the nth bit out to that register so that only that bit plane is active and nothing else. And then we do a straight up mem copy to the VGA memory plus the page that we selected, because the pages and the bit planes are of course separate. And we take the source pointer plus whatever bit plane we are on times 16,000, because that's how we shuffled it. And we copy 16,000 bytes. And that is a straight up very simple copy. So we only need 4 mem copies and only 4 bit plane switches, which is super efficient. In theory, you could already store the graphics in that format, even GIF compressed, which would make it even faster because you don't need to use the shuffle buffer and allocate extra memory. That would be preferable, actually, if you would jumble up your pixels in the data that you're going to load. All right, that's that. Now let's continue with the rest of the implementation. This should roughly build already with a couple of warnings and maybe an error. Yeah, exactly. Okay. There are still some things missing, and I think I mistyped set start address. Yes, I mistyped one function, which is better. Okay. Good. Let's start with the overflow registers. As I said, there are 2 registers that we need to save. This is the maximum scanline register, index 09 hexadecimal, and the overflow register, index 07. So I already defined those as static byte overflow and static byte MSL. Let's read them out. So we write to the CRTC index register, namely the value of the overflow CRTC register, which is defined in the VGA.h. You can look that up, or you can just write 0x07, obviously. And then we read that byte by calling import byte to the CRTC data register. And the important thing here now is that we want to end this with 0xEF, which is exactly so that LC8 should be 0 and the others should be 1. Let's check if that is actually the case. Can we switch here to a programmer view? I hope so. If we type in EF, we will see that we have 1, 1, 1, 0, 1, 1, 1, 1. 1, 1, 1, 0, 1, 1, 1, 1. Okay, that seems to be correct. This way, all the bits are set to whatever values they have, except for bit 4, which is forced to be 0. So we can toggle it with an OR later. Next up, we will do something very similar. So I will copy this. But this time it's not the overflow, but the maximum scanline register. And we'll do the same thing, except this time it's a different bit. And let's have a look. This time we want to select bit 6. Let's type BF. Oh, not like that. BF. And it's 1, 0, 1, 1, 1, 1, 1, 1. 1, 0, 1, 1, 1, 1, 1, 1. Okay, this seems to be also fitting. Bit 6 will be forced to 0, so we can easily turn it on or off with just an OR. Then we have stored all these values, which is fine. We only need to do 2 more things. Set the start address. The start address register is split into 2. The start address high, index 0C, and start address low, index 0D of the CRTC. This is easy enough. Again, just a couple of outport commands. CRTC index low address, address, and then the value that we got to CRTC data. And this is just simply the lower 8 bits. Very simple AND operation. And then let's type this out. Again to the CRTC index and then the high address. And now we just shift everything 8 bits to the right, and this gives us the high byte basically. And that's already changing the start address. With this simple thing you can do vertical scrolling. That's all you need. The set split is a little bit more complicated, but not by much. Here we need a couple of variables. I call the first thing LC low because this is the first register. This is basically just the line number that we got masked off with all the lower 8 bits kept. Then we have the value LC8. This is how it's also called in the documentation, which is equivalent to if we shift the line by 4 to the right, and then masking with 0x10. You can figure that out on your own, but basically we need to shift the 8th bit down so that it fits into our where is it maximum scan line register here, 07 and 09. So 07 has the overflow. Basically we need to shift it from bit 8, which is over here, 1, 2, 3, 4 values down, and then we end up here. And then again we have to mask that so that we only keep that bit, and that's actually 0x10. That is, we can type that. 10 in hex is 1 and 4 zeros, which is exactly right because we are the 5th bit, 1 and 4 zeros. This way we select only this bit. we can write that as move bit 8 to bit number 4, yes, bit 4 in overflow reg. Exactly, and then the same goes for LC9. And here again, conveniently shifting by right by 4, and then ending with 0xbf. And I think this is probably by design, because this shift by 4 is probably what IBM did on the VGA card in hardware. And BF again selects the correct thing, which moves bit 9 to bit 6 in MSL register. Okay, now we have prepared all the bits that we need to write. Now it's just a bunch of output operations. Again, CRTC index. Line compare is the easiest. That's the lower 8 bits. So we do output B to CRTC data of the LC low variable. Very simple. And now we can copy this whole stuff 2 times. And the next one is the overflow CRTC. And we write the value of LC8, obviously. But not like that, but ORed with the overflow value that we stored up here in the init overflow registers. Otherwise, we destroy the whole timing of the video mode, which would be very bad indeed. And the last one is the maximum scanline register. And again, we take the value of the MSL that we computed above and OR that with our new LC9 value that we computed here. Again, the MSL comes from up here, where we stored the static bits that are set for mode Y. And this, I think, should be everything you need. Let's see if it compiles. No warnings. Let's run it. No, let's not, because I did something stupid. And there we go, and we have an issue. Okay, let me find the mistake. There were actually 4 little mistakes. I'm not sure how many you spotted. The first mistake was that the input pointer for the shuffle frame, of course, has to start at in pointer plus I, because we have an interleave. Every 4th pixel is from the same bit plane. So for the next bit plane, we have to not start at the first, but at the first plus 1, 2, or 3. And then I had a typo here. I wrote 1600 instead of 16,000. That, of course, gave us only a 1/10 of the necessary pixels. The rest was garbage. That is now fixed. There were also a couple of copy and paste mistakes. The init overflow reg, that was probably pretty visible, had the overflow twice set, but MSL wasn't set at all. This gave us this weird scaling effect, which is nice. We should experiment with that. But yeah, that was inadvertent. And I forgot. Oh yeah, down here, LC9 has to be ended with 40, not with BF, of course, to select the 6th bit. I just looked in the wrong line in my notes. If we now compile everything, it should build just fine, and then we run it. And indeed, it works. These are the 2 screens. The split line is being moved up and down in a sine wave motion, being faster here and then slowing down and gently touching the bottom and the top. Yeah, this is 2 full VGA 320 by 200 images being displayed variably on the screen without having to copy any memory, just by setting the line compare register, so to speak. And this is simple enough. You could even do a scrolling in the background. Let's say you were putting something on pages 1, 2, and 3, then you could do a full 3 screen tall scrolling here as well. and also shift this thing around in the foreground. But that's it, I would say, for today. You learned how to use the maximum scanline register in combination with the line compare and the overflow register. We have learned how to read out those two extra registers and to manipulate single bits. We have again examined the low address and high address, which we have already used for the text mode scrolling. And you have seen how we can efficiently reshuffle graphics data so we can easily and quickly blit them to mode Y or mode X bitplane style memory. Yeah, that's it. Please feel free to remix this and this code and use it in your own productions. Yeah, until then, share, like, and subscribe. Follow me on Mastodon. The URL is chaos.social/@root42. There you can follow all my shenanigans. And I'll see you next time. Bye.